Suppose now that we have a 3-meter long massless rod constrained to rotate about this point with a 12 kilogram mass on the end. Now this is very similar to the situation you just saw where we had a mass on the end of a light rod. The difference is that there were masses on both ends of the light rod. Well, it's going to turn out that this situation is identical in its motion, at least, or in its angular acceleration, which is what we're after, to a situation where we had a 6-meter long rod with 6 kilograms on each end, constrained to rotate about the middle of the rod so that all 12 kilograms are at the same distance from the center. But for right now, let's just assume that we have 12 kilograms here, and we're applying a 30 Newton force. Well, we can easily conclude and quickly conclude that the 12 kilogram mass has to have an acceleration at this instant of 2.5 meters per second squared. That is, assuming that the 30 newtons is acting perpendicular to the rod. If the 30 newtons is acting parallel to the rod, there would be no acceleration. The 30 newtons would just be trying to compress the rod. If the 30 newtons has two components, one perpendicular, one parallel to the rod and one perpendicular to the rod, then only the component perpendicular to the rod is going to accelerate the 12 kilograms because the rod will prevent acceleration in any direction parallel to it. So, if this is a right angle, and it doesn't look like one, there's a little distortion due to the camera angle, and there's also a little bit of distortion due to the fact that I didn't draw the picture very well. I didn't really draw it as a good right angle, but it looks worse than it is. In any case, provided this is perpendicular, we do have an acceleration of 2.5 meters per second squared, and we ask, what is the angular acceleration? Now we use the letter alpha for angular acceleration, as you know. We can reason this out actually very simply if we understand what a radian is. Remember, a radian is an angle up here such that the arc distance traveled along the circle is equal to the radius of the circle. This thing is traveling in the circle of radius 3 meters, so 1 radian will correspond to a 3-meter distance along the arc. Now if we assume that this 30 Newton force somehow remains perpendicular as the weight goes around the arc, we see that the acceleration is always going to be 2.5 meters per second squared. 1 radian corresponds to 3 meters, so this constant 2.5 meters in the acceleration corresponds to 2.5 over 3 radians, or 0.83 repeating radians. So we can very quickly, if we understand what a radian is, and that a radian corresponds, in this case, since the radius is 3 meters, to a distance of 3 meters, we see that 2.5 meters is the same as 0.83 repeating meters, so the 2.5 meters per second squared is the same as 0.83 bar radians per second squared. Now that might seem a little bit slick, but that's actually a fairly good line of reasoning. However, let's take a look and put this on a little more rigorous basis. Let's take a look at what happens if we symbolize the whole process. If we have motion on a circle of radius r, an angle delta theta will correspond to a distance, an arc distance delta s, which is equal to the radius times delta theta. Again, if delta theta is 1 radian, then the delta s has to equal r, so this is certainly consistent. If delta theta was half a radian, then we'd have half of a radius of distance, and that's exactly what this would give us. So whatever proportion of a radian we have, well, that's what our angle is going to be in radians, and that's going to be the proportion of the radius that corresponds to the arc length. Under these circumstances, the average velocity of an object as it moves around here is the displacement over time. Now the displacement is measured along the arc. It's a delta s. But of course delta s is the same as r delta theta, so that the average velocity is r delta theta over delta t. But then we can factor out the r, and we can say that's r times delta theta over delta t. And what's delta theta over delta t? That's the angular velocity, the change in the number of radians change in angle over the number of seconds. So that we see that the velocity, the average velocity of anything moving around an arc of the circle here, is going to be the radius times its average angular velocity. Similarly, we can say that the average angular acceleration is the radius, or the average acceleration is equal to the radius times the average angular acceleration, which is what we essentially use over here. And in this case then, here we can say that alpha is a over r, because of course if a equals r alpha, alpha is a over r. But we don't have the bars over alpha and a here because now we're assuming uniform acceleration. But we're going to have 2.5 meters per second squared over 3 meters, over the radius 3 meters. And that again gives us our 0.83 bar meters per second squared, or radians per second squared, angular acceleration.